When I was a teenager, I came across a program called Ketman, which was written by someone called Pat Bryady. And this program is still one of my biggest influences as a programmer and also as an educator. The Ketman assembly tutorial was a Microsoft DOS application written for 8086 assembly. On the right, it has a simulation of a computer processor, and on the left, it has a long-form tutorial. Embedded within the tutorial are little snippets of assembly code that you can step through and see how they alter the state of the processor. The tutorial itself was written in a literary style by a person who was clearly passionate about their subject, but also had like a personality and really diverse interests. A few chapters in, there was an interlude, and I'm going to read it to you. At this point, I calculate that I've dropped the dolphins. I mean those delightful aquatic clowns that latch onto any passing ship and race alongside, thumbing their noses at human technology. Travelling between Cape Town and London in the 1950s, I was a little boy then, I remember being mesmerised by their antics. In the early mornings, the stiff breezes would heap the sea up into smoking crags, but they didn't mind that. Hour after hour, they would slice through the peaks and canyons and barrel out into the sunlight, as if to show that they could waste as much energy as they liked with gratuitous acrobatics and still have enough left to outrun anything a shipyard could produce. They never got bored with their sport, only calling off the race when their extraordinary sonar detected another and more interesting ship 10 miles away. He then compares these dolphins to people who perhaps pick up new interests or hobbies but lose interest quite quickly, download things and then throw them away and make you feel like you're popular even though you're really just getting kind of empty downloads. And so he ends this section with, "Don't quote me, but I think they're gone. My feeling is that I lost them several pages back with a ferocious burst of speed, and if you're still with me, it means you could be serious." The genius of this, just as the learner's mind may be starting to weary from learning the language that every other language was designed to save you from dealing with, the author turns to you and says, "I see you. I can tell that you're serious, that you're not like everyone else, just by making it this far. So let me tell you a bit about myself and then we'll go onwards." Through Ketman, I learned the stuff that programs are made from. It's arduous and annoying to trudge through, but it's not particularly complicated. And from the day that I internalized that, I knew that every program, everything a computer did came down to something like what I'd learned about assembly: memory, addresses, and instructions. Any software problem I had, I knew that if at the very least I was willing to trudge through the assembly layer, I could figure it out. If you've not got that level of understanding yet, Ketman may or may not be the thing that gives it to you, but spend enough time digging around in the guts of assembly and it will come. It's one of those languages that changes the way you think. When you realize that functions don't exist in assembly and that you have to figure out, if I wanted to build something like a function using these basic tools, how would I do it? Then you're really building an in-depth understanding of programming. So today I'm going to introduce assembly. I'm going to start off using Ketman to show you the execution model of assembler and of a processor in general, and then I'm going to show you some patterns using assembler that will run on Apple Silicon. I'll also be making 2 follow-up videos, one shorter one covering the same patterns in x86-64 for those of you who want to follow along but aren't on Mac or aren't on a modern Mac, and a longer one in which I'll demonstrate some more sophisticated assembly programs. Let's get started with some Ketman. To understand assembler, we're going to need to understand a simplified model of a computer processor. We're going to use Ketman to do this because I actually think it's still the best tool for visualizing a processor as it runs. Ketman uses 16-bit x86 assembly and it runs in a Microsoft DOS emulator. This is quite an ancient architecture now, but you can broadly imagine it as a simplified version of what still happens today. Don't worry too much about remembering all the precise instructions and details because the modern assembly you'll use will be different. Just try to take in the overall way it works. The actual assembly code is on the left. It's put together with 3 elements: instructions, labels, and directives. Instructions are the things like movcx30d and represent an operation for the processor to perform. They are the only things in this code that really exist in the machine code. Everything else is more for the assembler rather than the processor. Since assembler translates quite closely to machine code, it's also specific to a particular processor architecture. The list of instructions you can use on a particular processor architecture is called the instruction set. This is 16-bit x86 assembler, and it's largely forward compatible with modern x86 assembler. Apple Silicon chips use a different instruction set, which we'll see later. One of your key resources when assembly programming, particularly when you're learning, is a good instruction set reference. They can be a little hard to find, so this is a good one for x86. I'll put a link to it on the ODE's website. The next element is labels. Labels in Ketman are yellow. To understand labels, consider that if we were looking at a hex editor which could visualize machine code, each instruction would have an address. Labels are a way of giving names to addresses. Raw addresses are not just annoying for the programmer to use, they're also liable to change for any number of reasons. For example, if we added an instruction earlier on, this would shift all the addresses to be higher, and all of the addresses in our code would then have to change. So we insert labels at particular points in the sequence we want to refer to later. The assembler will then replace them with real addresses when it's assembling the code into machine code. That's what I mean when I say that they don't really exist in the machine code. They get swapped out by the assembler for the real addresses. Finally, there are directives. Here there's just one, ZSR, on the top line. A directive is a sort of side instruction for the assembler to do something specific. In this case, we're asking Ketman to reset the processor when it runs this line. And just like labels, they don't make it into the machine code. This code calculates the Fibonacci sequence up to a limit. I'll talk you through how it works in a bit. But first we're going to look at the representation of the processor on the right-hand side. We can imagine this in three parts: registers, flags, and memory. Registers are these things like AX, SP, DS, etc. You can imagine these as a fixed number of fixed size variables. Each register sort of has its own character. Some of them have a very specific purpose and can only be used for that purpose, like DS, which indicates the segment of memory that data is currently being read from. Whereas some of them are more general purpose, like AX, which you can broadly do what you like with. But even the general purpose ones have a kind of flavor, like a kind of idea to what they're supposed to be used for. AX, for example, stands for the accumulator register, and certain instructions will use it for that purpose. So there's a lot to be curious about. To the right of the top two registers, AX and BX, you can see the same data represented as decimal, binary, and ASCII. This is just a handy view that Ketman gives us. It's the same data, not anything new. You'll also notice that the IP register is blank. IP stands for instruction pointer, and together with the CS, or code segment register, it points to the next instruction to be executed. Since we're within an assembly interpreter, which simulates assembler rather than runs it directly, this isn't really a useful register to visualize. Suffice to say, in a real program, IP contains the address of the next instruction to execute, and it increments each time an instruction is executed. As always, there are some exceptions, but keep that in mind for now. Moving on to flags. Flags are indicated here with Ketman-specific symbols that I won't go too much into. They're each 1 bit in size and are either switchable to change the way the processor operates, or else they communicate small bits of information back to the program from a particular instruction. For example, if an operation produces a 0, the Z flag is set. So if we subtracted 10 from 10, then the Z flag will be set after that. The final part of this screen is memory. There are two mini windows here showing particular parts of memory, and this is more for us to see than part of the state of the processor. The first view, mem, is a little chunk of memory that we'll use later. The second, stack, is the first 12 bytes of the stack memory. It's also reflected to the right of the SS and SP registers, which determine where the stack is located. The stack has special behavior that we'll see later. I've also added a strip to the right of each memory window that shows us the same value in that cell in memory, but in decimal rather than hex. There are also some other bits and pieces related to Ketman which I won't go into, and in fact I'm going to blank out all of the stuff that's not necessary for us to see the program execute. And now we're going to step through the code. The first instruction, NOP, or null operation, does nothing, and the directive on the end tells Ketman to reset the registers. The next instruction, mov cx30d, moves the number 30 in decimal to the CX register. We're going to use this register to store the number that our Fibonacci generator should stop at when it reaches. The next instruction, mov ax0, moves the number 0 into the AX register to represent the first term of the Fibonacci sequence. Then push pushes the contents of the AX register onto the stack. The stack in this case is a simple structure that you can push values onto and then pop them off. When we run this instruction, the value of AX is written to the memory address pointed to by SS and SP, and then SP is decremented by 2 bytes. The stack, at least on this processor, grows towards lower addresses, and this does differ from processor to processor and from program to program. And we're pushing our sequence onto the stack just so that we can see it. It doesn't really have any other purpose in this program. We then do the same again with bx to set it to 1, the second term of the sequence, and push it onto the stack as well. We then have a label, myLoop, which doesn't execute, and then we use the add instruction to add bx into ax. This changes ax. We then push this new term onto the stack. We then add ax to bx, pushing it again. Then we use the cmp instruction to compare x, the lowest term we just generated, with cx, the limit. Directly following cmp in this case is the jb function, which stands for jump if below. It's a kind of conditional jump. So if ax is below cx, the execution will jump to the address of the label myLoop. Since ax is 1 and is below 1e, it does jump back and cycle around again. As we go around, we can see the stack build up the Fibonacci sequence until it exceeds 30 decimal and then stops. You may be wondering how JB gets its information from CMP. It's actually quite elegant. CMP subtracts CX from AX, but without changing the value of CX or AX. The operation does, however, alter the flags, which gives us information about the relative size of AX and CX. So, if they were the same, subtracting them will produce 0, and the 0 flag will be set. The 0 flag is not set, so we know that they're not equal. If AX was less than CX, then the result would be below 0. Now, our registers don't represent minus numbers directly. Instead, they wrap around to the highest value. When this happens, the processor sets a flag called the carry flag. There is another comparison that could set the carry flag to do with minus numbers, which I'm not going to get into right now, but we can guard against that by checking that CMP sets the sign flag to indicate that the result of the subtraction was a negative number. So if the 0 flag is unset, the carry flag is set, and the sign flag is negative, which means unset, then our question, was AX less than CX, is answered with true, and the jump happens. There's one more thing I want to show you in Ketman, which is setting arbitrary memory not related to the stack. And for this, I'm going to make the program set a memory address with the first Fibonacci number that exceeded the limit. Stepping through it again, it's all the same until we get to the first jump, which is now JA for jump if AX is above CX. If this is the case, then this will jump to write AX. If it isn't, then execution continues and we check bx, and then if the execution continued past that check, we do an unconditional jump back to the top of the loop. Think of this a bit like an infinite loop with a couple of break conditions. When bx does exceed 30, then we jump to write bx, which uses mov to write the value of bx to a memory address defined by the value of ds, which is the default segment in this case, plus the offset we've given it in the square brackets, which is 100. This is where our memory address just happens to be pointing so that we can see the result. We can now use larger limits and see the result of our code in the memory window. So that's broadly how assembler and machine code works. Essentially, all the code you've written over the years was compiled down to something that worked just like this, with instructions and registers and all that. And now you can see it. So if you can grasp how this kind of code works, you're going to have a ground floor understanding of how the higher level concepts in programming work as well. So by this part, I must have lost the dolphins. You're the serious ones, so welcome. We're now going to look at a more modern assembly dialect. You might actually want to skip to the exercises if you're so inclined and dip in and out of this next section as you need to. It's really useful stuff, but it can get a bit dense, especially if it's pure theory for you. Up to you though, you might just want to take it neat. Let's get into it. We're going to take a look at assembly for the AArch64 or ARM64 architecture, which is the architecture used by Apple Silicon chips. In a shorter follow-up video, I'll also show you all of this in x86-64, which is the most common architecture on non-Mac computers. The details will be different, but the core ideas are the same, so watch this one first. First, let's get a project set up. I've put together another toy template, which I'll link to on the ODES website. We'll also be using a more modern assembler. That's the program that assembles assembly into executable. In this case, we'll be using Clang's assembler, which is known as AS or AS. Our program is still made up of 3 elements: instructions, labels, and directives. In this assembly dialect, directives start with a period. This first one defines where our program should start by defining _main as a global. We then need to use the align directive to specify that our instructions should be aligned on 4 byte offsets. Remember how in the bitmap images video the rows had to be aligned on offsets which were multiples of 4? It's the same deal here. One thing that's actually kind of cool about ARM64's instruction set is that every instruction is 4 bytes long, so the alignment works pretty nicely. This isn't the case in other assembly dialects, as you'll see in the next video. Then we set up our label _ main. In modern assembler, labels end with colons. We don't have to indent, but we typically do. Then we have our instructions. The first instruction moves the value 1 into the register x16. Literal values, or as they're known in assembly, immediate values, are prefixed with a hash in ARM64 assembler. This is the first step of us setting up a system call, which is the only way our programs have to communicate with the operating system, even just to exit. For this syscall, we set the register x16 to 1 to indicate that the system call we want is the system call code 1, which is exit. The second instruction moves the number 77 in decimal into our register XO, which for this system call is the one that defines what our exit code will be. The third instruction, SVC or service with the argument literal hex 80, executes the system call. What does 80 mean? Nothing particular as far as I can tell. In fact, it seems to be totally ignored, but the docs say we have to set it to 80, so that's what we do. We run make run, which runs a set of commands in the template to build and run our executable, and then we see the result. It exits our program with exit code 77, which, since it's non-zero, is an error exit code. If we set it to 0, the success X code, then we see that reflected in the terminal too. Let's start building things up and look at the registers that are available to us with ARM64. You can pause and inspect this page a bit if you want, but I'll gloss the main points. Every register is at least 64 bits, and some of them are even more. For passing and returning data from subroutines, we use X0 through 8. We've got X9 through X15 for scratch work. That's whatever we want to use them for. And note that any subroutine or syscall we make might alter these, so they really are quite volatile. Then there are a couple of dangerous ones that we don't want to fiddle with. And then some more that we can use which will be preserved by subroutines that we call. And in fact, we have to find a way to store them and put them back when we want to use them in our own subroutines. There are also some special registers. There's the PC register or program counter, like the instruction pointer we saw before. There's the 0 register, which can store any number you like to any precision at any size, so long as it's 0. There's the stack pointer, which is similar to what we've seen before when working with the stack. And a flag register, but with only 4 flags: negative, 0, carry, and overflow. There's a link register used to store the return address of subroutines, and a frame pointer which is related to the stack pointer. There's also a load of floating point registers for floating point stuff, but we'll ignore those for today. So, key messages: there are a bunch of registers. We can use X9 through X15 for whatever we like. We can use X0 to X8 when we work out how to use subroutines, and probably X19 to 28 too when we work out how to be respectful with those. But X9 to 15 are all good, whatever, go wild. I'm now going to run us through a few patterns. Now, when you're programming normally, your cognitive process probably involves having to think about the problem, maybe breaking it down into bits and pieces that you can apply your programming tools to, like functions and objects and loops, and maybe even higher level operations like mapping. But one of the mind-bending things about assembly is that very little of that is available, very few of those tools. Now, on the one hand, this can give you a sort of annoying, how on earth do I even go about this feeling? But on the other hand, it's that feeling of problem solving, that exciting feeling, turned up to 11. Plus, you get the opportunity to learn how all of those high-level concepts translate down to the lower level. So that you can make the most of this without being totally rootless, I'm going to run you through some patterns for getting things done in assembly that map reasonably well onto what you already know. We're going to run through printing to the terminal, arithmetic, subroutines, loops, and conditional flow. And next time we'll probably cover a few more things as well. Now, these assembly versions might not be exactly what the equivalent C compiles into. They might not even be the most efficient, but they will help you get some traction in the quite muddy world of assembly. So let's dig in. We'll start off by writing to the terminal. Assembly programs running in the context of an operating system can only interact with the outside world via system calls. System calls are a request from our program to the operating system to do something on our behalf. We saw one of these with the exit code example before, and now we'll see it with printing to the terminal. Like before, we have our main and align directives, and then we have our main section which makes 2 system calls. The The first is going to print. We need to set up the registers before we call it. We'll set x0 to 1, meaning standard out, and we'll use the ADR or address instruction to load the address of greeting into register x1. If you know assembly, you'll note that we're taking a slight shortcut here by not using the data section and having the string right here along with the code. If you don't know assembler, don't worry about it for now. We then move the literal or immediate number 13 into the x2 register to be the length of the string, and then we call svc like before. This prints our string to the terminal. And then we execute our second system call to exit the program. So here's two system calls. If you want to take a look at some more, I'll link to a file which has, I think, a list of all of the big ones. The key things you want are their system call number, which is the first item, and their arguments, which you can see on the end. You pass these in an ordered way, starting from x0 and going upwards. Now, big warning here, these are considered private by Apple, not like top secret, but private as in you shouldn't really be calling them. If you use system calls directly rather than using the provided C libraries, then your code may break when the operating system is updated. This actually happened a little while ago to all Go programs because they decided they wanted to use the system calls directly rather than the C library. So if you're watching this from a cubicle somewhere and you're writing software to keep all of the tigers from escaping the zoos, do not do this. Go and do it the proper way. But since we're just playing around, we can do what we like. Moving on to arithmetic. This one is actually fairly straightforward. There are instructions for setting registers, adding them, subtracting them, and a lot more. There has been in the past a big disagreement as to whether the source or the destination register goes first, but in this dialect, the destination comes first. As I mentioned before, literal numbers are prefixed with the hash symbol and are called immediate values. They actually get encoded straight into the instructions. You may be interested to know that mov and mol aren't actually specific instructions by themselves, they're instead aliases to more flexible instructions. Mov is an alias for bitwise OR against the 0 register, since a bitwise OR of any value against zeros is just that value again, and mul is an alias for the MADD instruction, which means multiply add, which multiplies two numbers and then adds a third, except in our case, the third is 0. Like I said before, you'll want a good reference. Here's my favorite one, and I've linked it again on the ODE's website. Next, subroutines, or we might say functions. Neither subroutines nor functions actually exist in assembly, so we have to construct them ourselves. There are gradations of functions. A really advanced function might take and return arguments, support closures, and you can also pass it around as a value. A very basic quote-unquote function might not even return values. Since we're in assembly, we're going to have to start with the most basic kinds of functions that can fulfill our desire to have callable units of code. Let's call these subroutines. This is possibly the most basic we can get. It uses the B instruction, which stands for branch. It's unconditional and it just jumps execution to the address of our label, and execution continues from there. In this case, until the program exits. So that's fine. Let's take another example where we have two subroutines, which we call with B. The first to print hello and the second to exit. If we run this though, something goes wrong. Our execution just blazes through the end of our chunk of code and back into the main chunk, creating an infinite loop. So don't be fooled by the indentation. It's just instructions and labels here. Execution will flow down the sequence until we tell it to do something different. To fix this, we could create a go back label, which myPrint can then branch back to when it ends. This then resumes execution where we intended it, and our program completes successfully. Or we could reorganize our functions so that flowing down achieves what we want, with myExit coming directly after myPrint. These two approaches both have significant disadvantages. We lose control over the end of our subroutine. In this one, we have to exit afterwards, and in the previous, we always return to the same place. Either of these effects might sometimes be what we want, but often we want to return to wherever we called our subroutine from. There is an instruction that will help us achieve this result, BL, which stands for branch with link. It's like branch, but it sets register x30, also known as the link register, to the address of the instruction to return to. Then we use the instruction ret. It acts like an unconditional branch to the address that has been stored in the link register. This isn't quite as good as full functions because we can only return once. If we use BL and then BL again, we'll end up overwriting the address in the link register, meaning we'll end up only returning one step. We need to do more work to recreate the nice functions that we're used to. Perhaps you might even wonder at a few ways we could achieve this, but not right now. We'll cover that in a future video. Next, loops. probably you can already see how we're going to do this. Our main sequence starts, we pick x9 as our counter and set it to 0. Then we do our printing syscall as before. We increment our counter and compare it against 10 using CMP, which probably uses a similar flag-based logic as we saw in the Ketman section. Instead of JA or JB, we use BLT or branch if less than. There are a whole suite of these conditional jump instructions that you can find in the docs. Since 1 is less than 10, we go to the my loop label and cycle round again. When we're done with that, we fall through the end of the loop and call our exit subroutine. Technically, I guess this is more of a do while loop since the check is at the end, but that works fine for me. You can figure out a more traditional while loop with the test at the top if you like. Now let's look at conditions. Big lists of conditions are a little annoying to do in assembly, so it's a useful one to look at. Here we have a program that will print out one of 3 messages depending on how close we are to the end of the next minute. We kick off our sequence by calling my get seconds of minutes subroutine, which I'm not going to show you right now, I'll show it briefly at the end, and then we move the result from the return register x0 into our scratch register x9. I've structured our conditions with some labels, each with the prefix seconds and a double underscore along with a meaningful label. The first chunk is if there are less than 5 seconds left in the minute. First comes our conditional check. We compare x9 to 55. If x9 is less than 55, we skip this block by jumping down to the next conditional check. Otherwise, meaning that x9 is greater than or equal to 55, we print the less than 5 seconds to go message. Then, to avoid falling through, we branch to the end of our stack of conditions. We do this again for our second else if block, except with 50 rather than 55. Finally, we have our else block, which is going to execute if none of the others matched. We print the fallback message and jump to after the condition. We could just let it fall through, but I thought better to be explicit. Then we exit. Let's run through it again, visualizing the flow. If seconds is 59, then we execute all the way through the first condition and then branch to the end. If seconds is 52, we branch over the first condition block, then execute the second and branch to the end. If seconds is 30, we branch after both the first and second conditional blocks and then execute the else, and then finally we jump to the end. So each section has a label, a conditional jump, the block of code, and then an unconditional jump at the end. And here's the whole code, including my little subroutines and a few other curiosities you might find interesting. You might find when you're playing around with assembly that you can really easily get yourself into like a spaghetti-like mess. And you're not alone. This was a huge problem in the early days and actually inspired Edsger Dijkstra's famous article, Go-To Considered Harmful, which was all about the problems with go-to, branching and jumping and all that sort of stuff. The solution was something called structured programming, which was quite controversial at the time. It was the idea that programs should be structured based on the procedure that they were going through. So with ifs, loops, functions, and that sort of thing. It's hard to imagine that being controversial, but it was. In fact, I think someone published an article that was titled Go-To Considered Harmful in the 80s. Still trying to say we should have our go-tos, don't take our go-tos away from us. We'll get more into that in future as well. Back when I was introducing odes, I actually introduced it with 6 ideas, and I think with this video we've actually covered all of them. Let's see if I can remember them. Memory, yes, we spent loads of time on memory. Instructions, which has been a big focus of today. Functions, which we've now covered in the barest form. Structure, which we've just spoken about. Cognition, which we covered just briefly with this idea of patterns and breaking down programming tasks into patterns that you then in assembler have to build up from more primitive components. And system calls, actually that was the one I forgot. System calls, which we covered for the first time today. So we built up some pretty strong foundations. Very cool. Okay, so this video, like all others, comes with a page on the ODES website for resources and exercises. There's a list of useful links, including a toy assembler project template, as well as all the references to do with instruction sets and the other stuff I mentioned. And then there's a little section on how, if you want to get Ketman running yourself and do the old school tutorial, then you can do that. And there are also some exercises, fairly gentle this week. The first one is just to get you writing out your name, so really just enough to get you writing some assembly code. The next one is to print out some sequences and try out some different ways of doing that. There's also an exercise for members to whom I'm very grateful for supporting this project both financially and also with all of your lovely emails. That's it for this video. The next upload will be a shorter one, which will be focused on x86-64 assembler for those of you who need to work with that. And next week, a bigger video where I'll be tackling and demonstrating some bigger assembly projects, both in Apple Silicon assembly and in x86-64 assembly. See you then.